Hi, I'm Dela Cruz, and today I'm going to discuss one of the topics of properties of AV materials, the tensile properties. So what is tensile properties? Tensile properties vary from material to material and are determined through tensile testing, which produces a load versus elongation curve, which is then converted into stress versus strain curve. It is also composing of properties of material that has the ability not to fracture easily. Best example of this is the metals, because metals, they tend not to break easily when force is applied, but eventually they fracture when they pass the curve, which then they call the stress strain curve. So we will now go into the stress strain curve. Stress strain curve is known for it is the most reliable and complete source for the evaluation of mechanical properties of any fibers. It is also has different regions. The first region is the yield strength, and the highest of them all, or the maximum region, is the ultimate strength, and lastly is the fracture region. It is also has the two tensile forces acting on it, the stress and the strain. The stress-strain curve has two tensile forces, the stress and the strain. The stress has the formula of stress is equals to force over area, and as the unit of Pascal. And strain has the formula of strain is equal to delta L over L. It is unitless. And the stress-strain curve will be using also the Young modulus, and it has the formula of E is equal to stress over strain. So we will now going to yielding and yield strength. Yield strength is one of those tensile forces that can be located at stress-strain curve. It is the stress at which a material begins to deform plastically, and also the stress corresponding to the intersection of this line and the stress-strain curve as it bends over in the plastic region. Yield strength is measured as newtons per square millimeter or megapascal, and can be calculated using the formula yield stress is equal to force at yield over the original cross-sectional area. Yielding. It is the process of bending or stretching a material and not having the ability to return on its original form or shape. For example is when you pulling a wire at both ends, and when you are applying a equal force at each sides, and it is no longer returning to its original form or shape when you are remove the force you applied. Tensile strength. Tensile strength is defined as the maximum load that a material can support without fracture when being stretched, divided by the cross-sectional area of the material. It is also defined as the resistance of the material when force is applied. So, tensile strength can be calculated using the formula S is equal to P all over A, where S is the tensile strength, P is the force, and A is the cross-sectional area. So, one example of tensile strength is the nylon rope using in mountain climbing, because nylon rope cannot be easily broken or fractured when large amount of force is applied. So next is ductility. It is the physical property of a material associated with the ability to be hammered thin, or stretched into wire without breaking. A ductile material can be drawn into a wire. Examples are metals such as gold, silver, copper, erbium, terbium, and samarium. Resilience. Simply the ability of a material to absorb energy when it is deformed elastically, and release the energy upon unloading. It is also defined as the maximum energy that can be absorbed up to the elastic limit without creating a permanent distortion. So best example of resilience having a material having the property of resilience is spring. Next is toughness. Toughness is the area under the stress-strain curve. If the stress-strain curve is large, the material has a high level of toughness, and it can absorb large amount of force before fracturing. It is also the ability of a material to absorb energy and plastically deform before fracturing. It can be also calculated as the area under the stress strain curve. For a material who had a high level of toughness, it should have the equal balance of both ductility and strength. Low strength materials and brittle materials ended up having low in toughness and can be break and fracture easily. So now, we will going to discuss the stress strain graph. The strength of a material can be determined by a test known as the tensile test. In this test, the material is mercilessly pulled from both its ends. The relationship between the stress to which the object is subjected to and consequently the strain it suffers can be graphed, and this graph is known as the stress strain graph. This graph has different regions also, and those regions will be tackled later on. So we will now going to the regions of the stress strain curve. So the first region in the curve is the proportional limit. It is the point on a stress strain curve where the linear elastic deformation region transitions into nonlinear plastic deformation region. And next is the elastic limit. It is the point in the graph up to which the material returns to its original position when load acting on it is completely removed. Yield point. It is defined as the point at which the material starts to deform plastically. Ultimate stress point. It is the point with which represents the maximum point the stress can endure before failure. And lastly is the fracture or breaking point. It is the point in the stress strain curve at which the failure of the material takes place. So now we will be going to the sample problem. The problem is a 20 cm long tendon was found stretched 4.0 mm by a force of 14.0 Newton. Assuming that the tendon was approximately circular and has a diameter of 9.0 mm, calculate the Young's modulus under the tensile stress. So we have here the formula delta L is equal to 1 over E times force over area times L1. So L1 is the length of the tendon. So by deriving the formula to get the Young's modulus formula, we get the E is equal to F over A over delta L over L1, or the length of the tendon. So before we substitute the values of those units, of those givens, we need to write the given here. So I wrote the L1 is equal to 20 centimeters. So since centimeter the L1, we need to convert it to meter. So 20 meter is equivalent 20 centimeter times 1 meter over 170 centimeters. So we need to cancel the centimeter. We will be getting the value of 0.2 meter for our L1. So next is the delta L. For delta L has the value of 4.0 millimeters. So we need also to convert it to meter. 4.0 millimeter times 0.01 meter all over 1 millimeter. So we can cancel the millimeter. So the answer will be 0.004 meter for our delta L. And for area, we have the formula of pi times the diameter times 1/2. Since our diameter is 9.0 millimeter and it's circular, we need to convert first the diameter to millimeter since it is millimeter. So 9.0 millimeter times 0.01 0.001 meter over 1 millimeter. So we can cancel the millimeter. After we get the value, we need to multiply it to 1/2, so we get the value of area, which is area is equal to pi times 0.0045 meter. And we have the force acting on the tendon, 4.0 Newton. So after we convert them, we now proceed to the formula and substitute those values. And we will get the value of Young's modulus, which is 1.1 times 10 raised to 7 Newton per meter squared.